Tonight, as you settle into the gentle rhythm of evening, imagine a single drop of water floating peacefully in the vast Pacific Ocean. Not just any drop, but perhaps one that will soon embark on an extraordinary journey. A voyage that will take it from the depths of the sea to the heights of the atmosphere, across continents and through clouds, eventually finding its way to your windowsill as morning dew, or falling gently on your roof as tomorrow's rain. This is the story of one raindrop's incredible adventure through the endless cycle that connects all water on Earth. Our raindrop begins its journey in the deep blue waters of the ocean, part of an immense body of water that has existed for billions of years. Here, in the gentle sway of ocean currents, our droplet is surrounded by countless trillions of its companions, each one a tiny sphere of 2 hydrogen atoms bonded to 1 oxygen atom, H2O, the most essential molecule for life as we know it. The ocean where our raindrop rests is ancient beyond imagination. Some of the water molecules around it may have fallen as rain on the first continents, flowed through the rivers of prehistoric Earth, or been part of the vast inland seas that once covered much of what is now dry land. Others might be relatively new arrivals, having recently completed their own epic journeys from polar ice caps, underground aquifers, or the leaves of distant forests. In this peaceful aquatic realm, our raindrop experiences the gentle motion of ocean currents, those vast rivers within the sea that circle the globe like a planetary circulatory system. These currents are driven by a combination of wind, temperature differences, and the rotation of the Earth itself. The Gulf Stream, the California Current, the Antarctic Circumpolar Current. These are the highways of the ocean, moving water masses thousands of miles and connecting every sea to every other. As our raindrop drifts with these currents, it might travel extraordinary distances while remaining in the ocean. It could journey from the equatorial Pacific to the Arctic Ocean, or from the Atlantic to the Indian Ocean, carried by the great conveyor belt of global circulation. This journey might take decades or even centuries, as ocean currents move much more slowly than the swift atmospheric rivers our droplet will later experience. The temperature of the water around our raindrop varies depending on its location and depth. Near the surface in tropical regions, the water is warm, heated by the constant attention of the sun's rays. Here, water molecules move more vigorously, their increased energy making them more likely to break free from the liquid surface and rise into the atmosphere. But our droplet might also spend time in the deeper, cooler layers of the ocean, where the sun's warmth never reaches and temperatures remain just above freezing year-round. These temperature differences create a complex 3-dimensional circulation system within the ocean itself. Warm water tends to rise toward the surface, while cooler, denser water sinks toward the depths. This vertical movement, combined with the horizontal motion of currents, ensures that ocean water is constantly mixing, carrying nutrients, heat, and dissolved gases throughout the marine environment. Our raindrop is part of this living system. Dissolved within it and the surrounding water are minerals eroded from continents over millions of years. Sodium and chloride that make the ocean salty, calcium and magnesium from ancient rocks. Trace elements essential for marine life. The water around our droplet might contain nutrients that will soon feed microscopic phytoplankton, the tiny plant-like organisms that form the base of the ocean's food web and produce much of the oxygen we breathe. The ocean is also a vast reservoir of dissolved gases. Our raindrop contains tiny amounts of oxygen, carbon dioxide, and other atmospheric gases that have dissolved into the seawater. This dissolved carbon dioxide plays a crucial role in Earth's climate system, as the ocean absorbs enormous amounts of CO2 from the atmosphere, helping to regulate global temperatures over geological timescales. Life surrounds our floating droplet in forms both magnificent and microscopic. Whales might pass nearby, their massive bodies displacing millions of droplets as they navigate the oceanic highways. Schools of fish create shimmering, coordinated movements through the water. But even more abundant are the countless microscopic organisms, bacteria, plankton, and tiny animals that make the ocean their home. Our raindrop might temporarily become part of a microscopic organism's body, incorporated into its cellular processes, before being released back into the surrounding water. The surface of the ocean, where our droplet sometimes finds itself, is a dynamic boundary between the liquid water of the sea and the gaseous atmosphere above. Here, the interface is constantly in motion. Waves rise and fall, driven by winds that blow across thousands of miles of open water. These waves are more than just surface disturbances. They're expressions of energy traveling across the ocean, carrying information about distant storms and far-off weather systems. At the molecular level, the surface of the ocean is a place of constant activity. Water molecules are continuously breaking free from the liquid surface and entering the atmosphere as invisible water vapor, while others condense from the air back into the liquid ocean. Our raindrop exists in a delicate equilibrium at this boundary, sometimes part of the liquid sea, sometimes evaporating into the atmosphere, sometimes condensing back again. The salinity of the ocean water affects how easily our raindrop can evaporate. Salt water has a slightly higher boiling point than fresh water, which means it takes a bit more energy for molecules to break free from the surface. But given enough warmth from the sun and enough time, even the saltiest seawater will release its water molecules to the sky, leaving the salt behind as the pure H2O rises into the atmosphere. Seasonal changes affect our droplets' oceanic experience. During summer months in its hemisphere, increased solar heating makes evaporation more likely. Winter brings cooler temperatures and different weather patterns that might keep our droplet in the ocean longer. The angle of the sun, the length of days, and the strength of prevailing winds all influence whether our particular droplet will remain in the sea or begin its atmospheric adventure. As our raindrop floats in this ancient living ocean, it carries within its molecular structure the memory of countless previous journeys. The hydrogen and oxygen atoms that compose it were forged in the nuclear furnaces of ancient stars, scattered through space by stellar explosions, and eventually incorporated into the water molecules that make up Earth's hydrosphere. Our droplet is both ancient and eternally renewed, part of a cycle that has continued for billions of years. Tonight, as you rest in the comfort of your bed, our raindrop continues its gentle motion in the ocean's embrace, warmed by residual heat from the day's sunshine, surrounded by the vast community of water that covers most of our planet's surface. Soon, perhaps tomorrow or next week, the combination of solar energy, atmospheric conditions, and pure chance will lift our droplet from the ocean's surface and launch it on the next phase of its remarkable journey through the water cycle. But for now, it floats peacefully in the rhythm of the waves, part of the enormous interconnected system that makes life on Earth possible, waiting for the moment, rising to the sky, the dance of evaporation. As dawn breaks over the ocean's surface, something magical begins to happen to our raindrop. The first rays of sunlight penetrate the water, carrying with them the energy that will transform our peaceful droplet from liquid into vapor, launching it on an invisible journey upward through the atmosphere. The process begins gently, almost imperceptibly. Solar energy strikes the ocean's surface, and the water molecules around our raindrop start to move more vigorously. Think of it like a cosmic dance where the sun's photons are the music, and water molecules respond by moving faster and faster. As the temperature rises, even by just a degree or two, the kinetic energy of our droplet increases dramatically. At the molecular level, evaporation is a delicate balance of forces. Each water molecule in our droplet is held to its neighbors by weak bonds called hydrogen bonds, invisible threads that keep liquid water together. But as solar energy increases the molecular motion, some molecules gain enough energy to break free from these bonds. One moment, they're part of the liquid ocean. The next, they've transformed into individual gas molecules, lighter than air, ready to rise. Our raindrop doesn't evaporate all at once. Instead, molecule by molecule, it gradually transitions from liquid to vapor. Imagine our droplet as a tiny sphere of dancing particles, and one by one, the most energetic dancers at the surface break away from the group and leap into the atmosphere above. This process is so gentle that if you were floating on the ocean's surface, you would never feel it happening, though trillions upon trillions of molecules are making this transition every second across the vast expanse of sea. The invisible water vapor that was once our raindrop begins to rise through the atmosphere, carried by currents of warm air that form naturally as the sun heats different parts of the ocean's surface unevenly. These rising currents, called thermals, are like vertical rivers of air that can carry our vaporized droplet thousands of feet above the ocean in a matter of minutes. As our water vapor rises, it encounters the fascinating structure of Earth's atmosphere. The troposphere, the lowest layer where all weather occurs, extends from the ocean's surface up to about 6 to 10 miles high, depending on latitude and season. Within this layer, temperature generally decreases with altitude, about 2 degrees Celsius for every 1,000 feet of elevation. This temperature gradient will play a crucial role in our droplet's upcoming transformation. The rising air carrying our water vapor doesn't travel straight up like an elevator. Instead, it spirals and swirls, caught in the complex three-dimensional circulation patterns of the atmosphere. Our droplet might rise rapidly in a strong thermal, then spread out horizontally as it encounters a temperature inversion, then rise again as atmospheric conditions change. This vertical motion is part of the atmosphere's constant effort to redistribute heat from the warm equatorial regions toward the cooler poles. Other water molecules join our droplets' upward journey. Evaporation is happening continuously across the entire ocean's surface, with some areas contributing more water vapor than others. Tropical regions, where solar heating is most intense, send vast quantities of water vapor into the atmosphere. But even in cooler regions, evaporation continues, though at a slower rate. The total amount of water evaporating from Earth's oceans every day is almost beyond comprehension, approximately 1 trillion tons. As our vaporized raindrop rises higher, the air around it becomes thinner and cooler. The atmospheric pressure decreases with altitude, which means the air molecules are more spread out, with more space between them. This lower pressure allows rising air masses to expand and cool, a process that will eventually lead to our water vapor's next transformation. The cooling process follows a predictable pattern known as the adiabatic lapse rate. As our water vapor rises and the surrounding air pressure decreases, the air mass expands and cools at a rate of about 10 degrees Celsius per kilometer of altitude. This cooling happens not because heat is lost to the surroundings, but because the expanding air converts thermal energy into the work of expansion, a fundamental principle of thermodynamics playing out on a grand scale in the sky above. During its rise, our water vapor encounters other atmospheric components that will influence its journey. Dust particles, tiny crystals of salt left behind by evaporating sea spray, pollen grains carried by wind from distant continents, and even microscopic particles from volcanic eruptions or cosmic dust. All of these float in the atmosphere alongside our invisible droplet. These particles, called condensation nuclei, will become crucial players in the next chapter of our water's story. The atmosphere through which our droplet rises is not uniform, but stratified into distinct layers, each with its own characteristics. The boundary layer, closest to the ocean surface, is where our droplet experiences the most turbulence, as rising thermals mix with horizontal winds. Above this, the free troposphere offers smoother sailing, with large-scale wind patterns that can carry water vapor across entire ocean basins. Temperature variations in the atmosphere create invisible highways and barriers for our rising water vapor. Warm layers of air can trap moisture below them, creating temperature inversions that might temporarily halt our droplet's upward journey. Cold layers can accelerate condensation, while dry layers can actually cause water vapor to evaporate back into the surrounding air, a process that might temporarily disperse our droplet before it reforms elsewhere. The timescale of our droplet's atmospheric journey is dramatically different from its leisurely oceanic voyage. While ocean currents might carry water for decades or centuries, atmospheric transport happens much more quickly. Our water vapor might circle the globe in just a few weeks, carried by jet streams and other high-altitude winds that move at speeds of hundreds of miles per hour. Wind patterns guide our droplet's horizontal movement as it rises. Trade winds in tropical regions might carry it westward across the Pacific, The prevailing westerlies in temperate zones could sweep it eastward toward distant continents, or it might be caught in the circulation around a high or low pressure system, spiraling in great arcs that could take it on unexpected detours across the ocean or toward land. As our water vapor continues its ascent, it gradually approaches the altitude where the next phase of its transformation will begin. The cooling air can hold less and less water vapor, a relationship described by the concept of relative humidity. When air is saturated with water vapor and cannot hold any more, it has reached 100% relative humidity. Cool the air further, and the excess water vapor must condense back into liquid form. The height at which this condensation begins is called the condensation level, and it varies depending on the temperature and humidity of the air mass. On some days, this level might be just a few hundred feet above the ocean surface. On others, it could be several miles high. Our water vapor, which began its journey as part of a raindrop, floating peacefully on the ocean surface, is now approaching this critical altitude where it will once again become liquid water, but in an entirely new form. As our droplet nears this transformation point, it carries with it the energy it absorbed during evaporation, latent heat that will be released when condensation occurs. This energy, multiplied by the countless trillions of water molecules undergoing the same process, represents an enormous amount of power that drives weather systems across the planet. The evaporation and condensation of water vapor is one of the primary engines of Earth's climate system, redistributing heat and energy on a global scale. Tonight, as you drift towards sleep, our water vapor continues its upward journey, invisible and weightless, carried by currents of air warmed by the day's sunshine. Soon, perhaps within hours or days, it will reach the altitude where temperature and atmospheric conditions will trigger its next remarkable transformation. From invisible gas back to visible liquid, forming tiny droplets suspended in the sky that will eventually grow into the clouds above our heads. Birth of a cloud, the gentle return to liquid. High above the ocean, where the air grows thin and cool, our water vapor approaches one of the most beautiful transformations in nature. After its invisible journey through the warming atmosphere, our droplet is about to become visible again, joining with countless other water molecules to create one of the sky's most enchanting phenomena, a cloud. The transformation begins at a precise moment when the rising air mass carrying our water vapor reaches its saturation point. Think of air as a sponge that can hold different amounts of water depending on its temperature. Warm air is like a large, thirsty sponge that can absorb enormous quantities of water vapor. But as that air rises and cools, the sponge shrinks, and eventually it can no longer hold all the water it once contained. The excess water vapor must find somewhere to go. This is where the tiny particles our droplet encountered during its rise become essential players in the story. Floating in the atmosphere around our water vapor are microscopic specks of dust, salt crystals from evaporated sea spray, pollen grains, and other minute particles. These condensation nuclei, as scientists call them, provide surfaces where water vapor can begin to condense back into liquid form. Without these tiny anchors, water vapor might remain gaseous even in oversaturated air, creating an unstable condition called supersaturation. Our water vapor, invisible and gaseous, begins to cluster around one of these microscopic particles, perhaps a grain of dust that traveled thousands of miles from a distant desert, or a salt crystal left behind when a wave crashed against a rocky shore weeks ago. Molecule by molecule, water vapor condenses onto this tiny nucleus, each new arrival releasing a small amount of latent heat, the same energy that was absorbed when our original droplet evaporated from the ocean's surface.
The process of condensation is remarkably gentle. There's no sudden snap or dramatic change. Instead, our water vapor gradually transitions back to liquid form, creating a microscopic droplet so small that it would take millions of them to equal the size of the period at the end of this sentence. This newly formed cloud droplet is incredibly light, so light that it can float effortlessly in the air, suspended by the slightest air currents and thermal updrafts. As more water vapor condenses in the surrounding air, our tiny droplet finds itself in the company of countless others. Each droplet forms around its own condensation nucleus, and together they create a visible cloud, a collection of billions upon billions of microscopic water droplets, each one floating freely in the sky. The cloud appears white or grey to our eyes because these countless tiny droplets scatter sunlight in all directions, but each individual droplet is actually transparent, like a miniature version of the raindrop from which our journey began. The altitude where this condensation occurs determines what type of cloud our droplet will help create. If condensation happens relatively close to the ocean's surface, our droplet might become part of a low-hanging stratus cloud, creating a grey blanket that hugs the horizon. Higher up, it could join a puffy cumulus cloud, those cotton ball formations that drift lazily across summer skies. At even greater heights, our droplet might contribute to the wispy ice crystal formations of cirrus clouds. Though at those frigid altitudes, it would freeze into ice rather than remaining liquid. The cloud that embraces our newly condensed droplet is a dynamic, ever-changing environment. Air currents within the cloud create circulation patterns that can carry our droplet up and down, sometimes rapidly. In the upward moving portions of these currents, our droplet might encounter more water vapor condensing around it, causing it to grow larger. In the downward moving areas, it might partially evaporate, shrinking in size as some of its molecules return to vapor form. Temperature variations within the cloud affect our droplet's behavior in fascinating ways. In the warmer, lower portions of the cloud, water droplets remain liquid. But if air currents carry our droplet to higher, colder regions where temperatures drop below freezing, it might freeze into an ice crystal. These ice crystals have different shapes and behaviors than liquid droplets, and they can grow much larger as water vapor deposits directly onto their crystalline surfaces, a process called sublimation. The cloud surrounding our droplet is not isolated from the rest of the atmosphere. It's constantly exchanging moisture, heat, and energy with the surrounding air. Along the edges of the cloud, some droplets evaporate back into the drier surrounding air,
while new condensation occurs where fresh water vapor encounters the cloud's interior. This constant turnover means that clouds are never static. They're always forming, dissolving, and reforming as atmospheric conditions change. Other forces also influence our droplets' experience within the cloud. Electrical charges can build up as ice crystals and water droplets collide within the cloud, creating the conditions for lightning. These electrical forces can affect the behavior of individual droplets, causing them to move in ways that purely thermal or gravitational forces cannot explain. During thunderstorms, our droplet might find itself part of a dramatic electrical environment where the entire cloud becomes a generator of atmospheric electricity. The size of our cloud droplet determines how it behaves within the cloud's internal circulation. Tiny droplets, like ours initially is, are easily carried by air currents and can remain suspended for hours or even days. But as droplets grow larger through continued condensation or by colliding and merging with other droplets, they become heavier and more likely to be affected by gravity. Within the cloud, our droplet may encounter others that formed at different times and places. A droplet that condensed from water vapor that evaporated from a tropical ocean might merge with one that originated from a mountain lake, or one that was exhaled by a forest halfway around the world. Each collision and merger adds to our droplet's mass and changes its characteristics slightly.
The cloud's movement across the sky carries our droplet on a horizontal journey that can span continents. High-altitude winds, including the powerful jet streams that circle the globe, can transport clouds thousands of miles from where they first formed. Our droplet, which began as ocean water off the coast of one continent, might now be floating in a cloud above an entirely different landmass, perhaps approaching mountains, forests, or cities it has never encountered before. As our droplet drifts within its cloud, it experiences the constant interplay between condensation and evaporation that keeps clouds in a delicate balance. When the cloud encounters drier air, some droplets evaporate, making the cloud smaller or causing it to dissipate entirely. When the cloud moves into more humid conditions or encounters additional water vapor, new droplets form and existing ones grow larger. The journey within the cloud can last anywhere from minutes to days, depending on atmospheric conditions and the cloud's life cycle. Some clouds form and dissolve quickly as atmospheric conditions change. Others persist for extended periods, slowly evolving as they travel across the sky. During this time, our droplet remains in a state of constant potential change, always ready to grow larger, evaporate away, freeze into ice, or begin the next phase of its journey toward the earth below. As you settle into the quiet comfort of evening, our droplet floats peacefully within its cloud, part of a vast aerial community of water suspended between earth and space. The cloud drifts slowly across the darkening sky, carrying our droplet toward whatever landscape lies ahead. Soon, when atmospheric conditions are just right, our droplet will begin the next remarkable phase of its journey, growing large enough to overcome the air currents that have kept it aloft and beginning its descent back toward the surface of our planet. Growing in the sky, the art of precipitation formation. Within the gentle embrace of its cloud, our tiny droplet begins a remarkable process of growth that will eventually transform it from a microscopic speck of water into something large enough to fall from the sky. This transformation happens through a delicate dance of physics and chemistry that has been perfecting itself
in Earth's atmosphere for billions of years. The growth begins almost imperceptibly. Our droplet, still incredibly small, drifts through the cloud's interior, where it encounters other droplets of various sizes. In the seemingly chaotic swirl of air currents within the cloud, these encounters are not random, but follow predictable patterns governed by the laws of fluid dynamics. Larger droplets tend to fall slightly faster than smaller ones, even within the cloud's circulation, creating opportunities for collisions. When our droplet encounters another droplet, something beautiful happens. If the collision is gentle enough, the two droplets merge, combining their water molecules into a single, larger droplet. This process, called coalescence, is like two soap bubbles joining to form one. The surface tension of water, that invisible force that gives droplets their spherical shape, helps hold the newly combined droplet together as it continues its journey through the cloud. Each collision and merger makes our droplet slightly larger and slightly heavier. With increased size comes increased gravitational pull, though at this microscopic scale, gravity is still much weaker than the air currents that keep the droplet aloft. But slowly, incrementally, our droplet begins to respond more to downward gravitational force and less to the upward air currents that have been supporting it. The cloud's internal circulation creates different environments for droplet growth. In the updraft regions, where warm air rises rapidly, droplets are carried higher into the cloud, where they encounter different temperatures and humidity levels. These updrafts can be surprisingly powerful. In some clouds, air rises at speeds of several meters per second, easily carrying even relatively large droplets upward against gravity's pull. In the downdraft regions, cooler air descends, bringing droplets toward the lower portions of the cloud. Here, our growing droplet might encounter different conditions, perhaps warmer temperatures that increase evaporation rates, or different concentrations of water vapor that affect how quickly it can grow. These vertical movements within the cloud create a complex three-dimensional mixing process that brings droplets of different sizes and histories into contact with each other. Temperature plays a crucial role in our droplets' growth process. In the warmer lower regions of the cloud, growth happens primarily through coalescence, droplets merging with other droplets. But if air currents carry our droplet to higher, colder regions of the cloud, where temperatures approach or drop below freezing, an entirely different process can begin. In these colder regions, our droplet might freeze into an ice crystal, or it might encounter existing ice crystals formed from other water droplets. Ice crystals have a remarkable property. They can grow much more rapidly than liquid droplets. This happens because water vapor deposits directly onto ice surfaces more readily than it condenses onto liquid surfaces, especially at temperatures just below freezing. This process, called the Bergeron-Findeisen process, can cause ice crystals to grow dramatically, while nearby liquid droplets actually shrink as their water vapor transfers to the ice. If our droplet becomes part of this ice crystal growth process, it might form beautiful, intricate shapes: six-sided snowflakes, needle-like crystals, or tiny frozen spheres called graupel. Each ice crystal's shape depends on the exact temperature and humidity conditions it encounters as it grows. No two snowflakes are exactly alike, because each one experiences a slightly different journey through the varying conditions within the cloud. The collision process becomes more efficient as our droplet grows larger. Bigger droplets have larger cross-sectional areas, making them more likely to encounter and collect smaller droplets in their path. They also fall faster through the air, even within the cloud's circulation, increasing the rate of collisions. This creates a positive feedback loop. The larger a droplet becomes, the faster it can grow even larger. Wind shear within the cloud, differences in wind speed and direction at different altitudes, can affect how droplets collide and merge. Strong wind shear might break apart larger droplets that have grown too large to maintain their spherical shape, while gentle wind patterns can enhance the collision process by creating favorable conditions for droplet encounters. Our growing droplet also benefits from the cloud's overall water budget. Clouds are constantly gaining water through condensation of water vapor and losing water through evaporation at their edges. When a cloud is in a growth phase with more condensation than evaporation occurring, droplets throughout the cloud have abundant opportunities to grow. When the cloud is dissipating, droplets might actually shrink as water evaporates back into the surrounding drier air. Electrical forces within the cloud can also influence droplet growth. As ice crystals and water droplets collide within the cloud, they can transfer electrical charges, creating regions of positive and negative charge separation. These electrical fields can affect how droplets move and collide, sometimes enhancing the growth process by attracting oppositely charged droplets together. The timescale of this growth process varies dramatically, depending on cloud conditions. In some clouds, particularly those with strong updrafts and high water content, droplets can grow from microscopic size to raindrops in just minutes. In other clouds with gentler circulation and lower water content, the growth process might take hours or even days. As our droplet continues to grow, it begins to take on the characteristic shape of a falling raindrop, upon the teardrop shape often depicted in drawings, but a more complex form that's somewhat flattened on the bottom due to air resistance. Small droplets maintain their spherical shape due to surface tension, but larger ones become increasingly distorted by the forces they encounter as they move through the air. The size our droplet ultimately reaches depends on many factors: the cloud's water content, the strength of updrafts, the temperature profile within the cloud, and the presence of ice crystals. Some droplets grow large enough to become raindrops, while others might remain small enough to drift as drizzle. Still others might freeze and fall as snow, sleet, or hail, depending on the temperature conditions they encounter, both within the cloud and during their descent to Earth. Throughout this growth process, our droplet carries within it the molecular history of its journey. The water molecules that compose it might include some from its original oceanic beginning, combined with others that joined during various condensation events. Some molecules might have been part of other droplets that merged with ours during the collision process, each bringing their own story of evaporation, atmospheric transport, and cloud formation. As our droplet grows heavier, it begins to respond more strongly to gravity's pull. The upward air currents that once easily supported its microscopic mass are gradually overcome by its increasing weight. It starts to sink lower in the cloud, toward the cloud base, where it will face the ultimate test. Can it maintain its integrity as it leaves the protective, humid environment of the cloud and enters the drier air below? Tonight, as gentle breezes stir the air outside your window, our droplet continues its growth within its aerial nursery, slowly accumulating water molecules and preparing for the next phase of its remarkable journey. Soon, when it has grown large enough and heavy enough, it will begin its descent from the sky, falling through layers of atmosphere toward whatever landscape awaits below. Perhaps a forest, a city, a field, or even back to the ocean from which its journey began so long ago.